Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. Previously in All Things Photonics, we shared some of our conversation with Joel Rothman, Director of Biomolecular Science and Engineering at the University of California, Santa Barbara. In our interview, Rothman introduced us to Project Starlight. The multifaceted, multidisciplinary NASA program aims to take invertebrate organisms, namely nematodes and tardigrades, and launch them into space. There's more to the work than that, but the gist insofar as the biological portion of the project is concerned is that quite a lot of our own behavioral patterns as humans can be predicted by these tiny organisms. That's part of what makes Project Starlight so fascinating. Just getting these creatures into space is no small feat. Today, we bring in the man on the other side of Project Starlight. Philip Lubin directs the Experimental Cosmology Laboratory, Space Research Laboratory, Interstellar Center at UCSB. He also heads the directed energy component of Project Starlight, that is, the photonics component. To classify his role in the project as no small feat doesn't even begin to convey the scope of what Lubin has on his plate. Plainly put, adapting large-scale directed energy applications for interstellar missions is hard. It's wildly expensive, mathematically daunting, mechanically demanding, and yet, somehow, theoretically possible. In our conversation, Lubin breaks down Project Starlight into individual photonic goals. The work may not become simpler, but it does begin to make sense, both in terms of how and in terms of why. For Lubin himself, this pillar-by-pillar approach is the way to view the project. Propelled by interconnected innovations in the photonics landscape, the individual accomplishments that are needed to achieve Project Starlight's ultimate end goal are ripe with real-world applications. They fall into the areas of data communications and optics, metrology and high-powered lasers, and, as you'll hear, much, much more. Part 2 of our look at Project Starlight is next.
All right, so Drs. Joel Rothman and Philip Lubin from the University of California at Santa Barbara are our guests today. They're here to discuss the kind of work that I suspect a very select few researchers are able to call their own. They are at work on a project that intends to place invertebrate organisms on wafer-scale platforms and launch them into space. Not in and of itself photonic until you realize that the guests plan to deploy directed energy arrays to achieve that goal. Making assessments on the impact of interstellar travel, of course, on humans sometimes starts small, although I hesitate to call this work small. My first question, and this is for both of you, we'll start with you, Phil. What exactly is Project Starlight?
Project Starlight is a NASA program in a very early stages. It's not a large scale formal program. It started around 2009 with what we call NASA Space Grant funding, which is designed to cultivate innovative ideas involving lots of students. So we took on a task that was related to some work I was doing on scaling of smaller phased arrays, of optical phased arrays. And we looked at the consequences of what would happen if we scaled them up to extremely large sizes, say of order kilometers or more, and we're able to project huge amounts of power, sort of, of order hundreds of gigawatts of power, at least for short periods of time. So that was a technological question, but the interest on our part was what would be the consequences of such a platform in terms of advanced propulsion systems, both driving high-performance ion engines at a distance, so you don't have to carry as much mass with you to power them, because you can broadcast the power remotely and over vast distances. So very practical things. That's what I would say is a moderately low-hanging fruit part of the program. But then ultimately, if you look at the long-term consequences, which is what really interested me, was that the things that we now assume are just not possible in the realm of science fact, but are more the realm of science fiction movies, such as interstellar capability. So the ability to achieve relativistic flight. So I'm trained as a field theorist in physics. So I do enjoy science fiction as a pastime, but my day job is very much mathematical and physics oriented. So for me, the concept of relativistic flight is a purely mathematical and physics based issue. It's not where's the warp button and we'll assume miracle happens here. This is very much a problem rooted in really a question of phase convergence. How does one phase lock and then phase converge a large number, in our case, a MOPA architecture, which is a master oscillator power amplifier. So sort of a classical phased array approach, similar to what is done with phased array radar systems, except we're using near infrared, not millimeter or centimeter wave radiation.
Right away, we should mention that directed energy, for Lubin's purposes, does not refer to anything involving applications in defense and aerospace. And that poses a bit of a challenge given the nature of that field's evolution and of how DE systems are commonly deployed. The first challenge of many that Lubin fleshes out stems from the fact that ground-based systems are prone to the effects of atmospheric turbulence. Resolving that is a key bottleneck in practical deployments of directed energy.
So the problem actually starts from a basis of one uses directed energy primarily in a DoD context for tactical systems, and there have been musings about using it more on a strategic level. But typically, the field has evolved into the point where it's much more complex to deploy it in a practical, say, battlefield arrangement because of primarily atmospheric problems. If you're going to use something to take down a drone, not so bad. If you want to take down a cruise missile or an incoming ICBM, much more complex for an in the atmosphere or ground-based system, particularly because you don't always have conflicts on clear days where the CN squareds are low. And so for me, this was the real set of questions. It was very much rooted in atmospheric turbulence questions if it were going to be ground-based. And ideally, it would be space-based, either orbital or lunar were the two natural places to place such an array. And then how does one converge the phase on a large number of elements? And I was very much plugged into various things that were happening on the other side of the fence in terms of what people were working on, interested in for small systems on the tactical level. And, there they had really only scaled up to quite small systems with, modest power levels. And there was kind of a, aha moment that happened around 2009 or so when I was at a conference looking at, more classical uses for directed energy. And at that point, I started to ponder, why can't we scale this? What is preventing us from scaling it to massive architectural sizes, which frankly were not of such great interest to the DoD sector because it's not a portable system that would be used in a typical battlefield arrangement. But it would be an amazing system from the space research point of view if you could pull it off. So this was not just some wild flight of fancy, which often happens in the realm of interstellar. So, interstellar has a bad name for a good reason because there's a lot of bad science out there associated with it. And usually it's miracle happens here kind of thing. But this was really a very practical approach from my point of view of what would prevent us from doing it and what were the real tall poles to pulling this off. And it was clear to me that there were a number of technological tall poles, and then there was a huge tall pole of economic scalability. And the thing that I really wanted to look at was a long-term approach, a multi-decadal approach, much like the semiconductor industry has for their semiconductor roadmap approach to technological advancement in electronics, is that photonics, is also an exponential growth area and shares many of the commonalities with the electronics exponential growth, the so-called Moore's law And when I started looking at the performance of photonic based systems, particularly in the laser world, and their cost as a function of time per metric, which could be, say, power out of a single mode fiber, was just one metric, or cost per watt for pump diodes, and performance, as a function of time. So I started plotting these just out of curiosity, and worked with some of my colleagues in various other labs that do programmatic related work. There was actually an exponential growth, and it has a very close to a Moore's law timescale. So it was doubling in performance and halving in cost on timescales over were 18 to 24 months. Very much like electronics, and not for any reason of specific commonality that photonics and electronics use the same processing. They don't. They have similarities, yes, but they're not fundamentally the same. But just coincidentally, they're both these extremely rapid growth areas, driven not by the government, not even by the DoD interests, but by consumer interests. And that's something which has to be injected, at least from my part. This is a very important point, is that this area is driven by consumer level needs for high-speed data, for lighting, for efficient use of lasers for industrial processing, medical uses. You can just look at it, and your readers would appreciate this, is that this is an enormous growth area.
An industrial and consumer base is pushing the work that Lubin describes. While his own sights may be set on the outer reaches of the galaxy in one sense, he is in another solving a series of smaller problems in photonics. In his group's lab, Lubin's optical table looks like any other that you might find in an applied or theoretical research environment. Sprinkled into our conversation about starships and interstellar mathematical calculations are mentions of more familiar components, like diodes, fibers, amplifiers, and shifters. What stands between an initiative like Project Starlight and the ability to ride the forceful wave of a consumer photonics base is the need to phase an unprecedented number of laser amplifiers, and also some funding.
There's a semantics issue here. When we talk about a phased array of lasers, it is really very similar to a phased array in a radar system. As you start with a local oscillator, in our case, it's a seed laser. And then in both cases, you split the local oscillator, amplify, phase shift, and then have an emitter section, and then you phase converge in free space. So this is the way that many phased array radar systems work, and you can see them deployed. You just Google phased array radar system, and you'll see it. So in a very nascent stage, this is where phased array optical systems are. And some have been built, and they're basically small scale, and some have even been deployed for specific needs, mostly DoD needs. So this is the fundamental question, and this is where most of our group's effort is focused, is the both mathematical and technological question of large-scale phase convergence in a MOPA architecture. The consequences of that are all these incredible things that Joel and I are interested in, among many others. And some of the others are really interesting to think about, such as it takes us of order 9 months to get humans to Mars using chemistry. We'd love to get humans to Mars faster if we could. One approach to get humans to Mars that we published a long paper on is to use the same architecture to project power, which is really all that we're doing. We're fundamentally just projecting power, in our case, in the form of roughly 1 micron photons. But you could project it over ranges that are relevant for space applications. So in the case of going to Mars, one approach that you could ponder in your mind is you project power, leave your power source at home, whether on the moon or on the Earth. And we can get it to atmospheric perturbation issues, which are a major issue, but talk about that in a bit. But if you can project power over relevant ranges, and relevant in this case would be sort of astronomical ranges within the solar system, then one could power high ISP, high specific impulse ion engines on a mission, and then get things, including humans, to Mars, and including slowing down and going into orbit, which is very important for humans, not just flyby missions, in of order a month instead of 9 months. And that becomes a fundamental game changer in space research if you can do that. So there are many applications here, and I don't want to purely look at this from the point of view, I prefer not to in this podcast, of relativistic interstellar capability, but rather this is a question of power projection and the consequences that occur from that.
Just as you're beginning to think that there couldn't possibly be any more room for optics and photonics in this endeavor, we remind you that this work also involves another altogether separate branch of science. Joel Rothman, who joined us on an earlier episode of the podcast, leads the biological component of the research. His partnership with Lubin and the rapport that the collaborators have developed are keys to Project Starlight's big picture.
Actually, a lot of people say that academics and particularly physicists have their heads in the clouds. And in Phil's case, that is totally not true. His head is way above the clouds.
In the ground.
No, way above the clouds. So actually, I had heard him talk about this for a number of years and seeing some press releases on it and was fascinated, but it hadn't clicked in, I think, until I went to a talk that Phil had given here on campus. And I worked with his daughter in a different project, actually, and she had mentioned that Phil was going to be doing that because I told her about my fascination with this project and heard him talk. And it just sort of clicked. I guess there was an aha moment for me that, in fact, if Phil could actually get this technology to work, we could hitch a ride, basically put a miniature lab on board one of these star chips as it's flying along at 20 to 40% C. And knowing that I've for years worked on small organisms that certainly would easily be accommodated in such a craft, I realized we could ask an enormous number of questions about biology, not only the simplest questions like biochemistry, cell division, and so forth, but actually questions about how behavior and memory are affected by traveling between star systems. I think an important question to answer if we're ever ourselves thinking of venturing out there.
Just want to add a quick point. I believe Joel and I met at the 50th anniversary discussion of Star Trek.
That's right.
I think that's where we met.
Fitting, yes.
And yeah, it's very fitting. And I didn't know Joel, although I actually knew of Joel's name, but I'd never met Joel before. And there was a person in the audience who started asking all these really intelligent questions, and turned out to be Joel. So there's a couple classes of bottlenecks. One is the mathematical problem of phase convergence of very large number of elements. So this is very much a difficult mathematical and to some extent technological problem, but it's really, I would say, more of a mathematical problem. How do you phase converge so that you have, high Strel on target, if you will, in the photonics language, a large number of, physically independent objects that share a common local oscillator, common seed laser, but are drifting independently of each other from all kinds of fluctuations in their fiber. It's a fiber-based system rather than a free space-based distribution system. So the distribution is all done in fiber. And then the amplification, in our case at the moment, is done in fiber. So we build our own fiber amplifiers in our lab. So we have that under control, and they're around 43 to 47% efficient. So that box is checked. We build amplifiers that have very long coherence length. So they have coherence length basically set by the line width of the master oscillator, which is another fiber-based laser in our system. So that's around 10 kilohertz. So it's around 30 kilometer coherence length. So that's a key element. You have to get the coherence length of the sub-elements to be comparable to the array size. And for physics and mathematical reasons, our array size needs to be of order 1 to 10 kilometers for the basic system. So that's way outside the parameter range of tactical systems, which are basically a rigid optical element. Our system is not a rigid optical element. It is a distributed optical element. It's close packed array, but because of the size, it's distributed. So coherence length is a major issue. We've solved those two already in our lab. But the key technological problems are this problem of convergence. We may in the end have billions of elements, so billions of emitters. And for a ground-based system, you don't want the emitter to be very large because of perturbation issues in the atmosphere. So it's typically known as the Fried length in language of atmospheric perturbation. So for a high altitude based site, like an astronomical site, we would typically have a free length at our wavelength on good days with CN squareds that are of order 10⁻16 at the ground level, that are roughly of order 20 centimeters or so. So we keep our optics at about the 10 centimeter diameter scale. Now you can go larger, but then you have to have adaptive optics, higher order adaptive optics on every sub-element. So very complex. We don't do that. We do a tip tilt on every sub-element, but not high order corrections. The high order corrections are done by keeping that sub-aperture small, and then by doing the higher order corrections in the phase control of each individual sub-element. So then it becomes this mathematical complex problem of phase convergence on very rapid timescales, because the atmosphere is not waiting for you to figure out what the right phase should be. You have to phase converge in of order a tenth of a millisecond or so. And that is an unsolved problem at the moment, one that we have analytically showed should work based on, we have a nested tree architecture for phase convergence, because you can't do it with the same, well, we don't know how to do it with a single non-nested loop architecture. But mathematically, we've shown that this works. Then we've done simulations, and it works in simulation. And we've done 2 deep nested loop architectures in our lab so far. So far, that part is working, but that is the key technological problem that we must overcome in order to make this program realizable.
In photonics, conversations about space imaging tend to introduce adaptive optics fairly quickly. Lubin mentioned them earlier, though they aren't a focal point of the work in its current stages. The bottlenecks that Lubin just discussed correspond to a ground-based system only. Should Lubin successfully manage to ascend Project Starlight into space, atmospheric disturbances fall away. They give way to system-level challenges, and those too can be resolved using photonics.
If you go into space, which is a more natural home for this technology, then you remove the atmospheric perturbation, and then you're left with system-level perturbations, of which there are fiber fluctuations, metrology, things are bouncing around, this microphonics, it doesn't matter how well you build the system, thermal fluctuation, et cetera. So you still have to overcome those in a phase convergence architecture. But those are of a very different power spectrum than does the atmosphere. They're much more benign if we go into space. But no one's going to fund us to go into space until we show at least that it works, pretty well on the ground in a relevant environment, so we get the TRL level up high enough. So I would say if there's one key technological problem, that is the key technological problem. We have already shown that we can phase converge in the absence of the atmosphere down to a level of better than lambda over 100 over baselines exceeding 10 kilometers in baseline. And that was a key moment as well for us.
The 10,000-pound elephant in the room is one that Lubin has yet to discuss, the economic factor. Or more plainly, the cost. Human interstellar travel is expensive. As it turns out, this is also the case for nematodes and tardigrades. Earlier, Lubin described the approach that he is taking for Project Starlight. By knocking down one pillar at a time, a fantastical dream starts to become a reality.
There's a second level of difficulty, which is not so much a technological one, but this economic one. If you ask, well, how much money does it cost to build this system at the current time, the cost, even when we build things ourselves, is still much too high to be afforded in a sort of conventional sort of, NASA budgetary environment. So we would be much more expensive than JWST, which is coming in at $10 billion. We would be much more expensive than that if we had to build at the current level of economic capability, i.e. the cost, per watt, cost for, various things like lithium niobate phase shifters. Our lab is basically, you come to our lab and our optical table looks like any other optical table. It's a gigantic mess of optical elements, fibers all over the place, amplifiers, optical systems, beam splitters, phase shifters, et cetera. It's not like electronics where you pick up a modern microprocessor and you look at, oh, it's beautiful. Look at look how beautiful they designed the wafer. Photonics is not yet at the integrated photonics level on wafer. People are working towards that. And some of our colleagues in engineering, like John Bauer's group, are masters at trying to build to this level of integrated photonics. That's one of the necessities of the success of this program, is driving down the economic cost to the point where it's feasible and affordable to build. What we have built in our lab is a system that simultaneously outputs high power, like a normal laser amplifier, and will simultaneously amplify low power. So we can amplify at the tens to hundreds of watt level going out, and we can, that's outbound, but we can simultaneously, not time gated, so not time sharing, but full bidirectional. We can simultaneously amplify at the sort of 100 picowatt level coming in. So we've achieved a dynamic range in excess of 110 dB, or 100 billion to 1, and we're not done yet. We're pretty close to photon statistics limited. So that's been a milestone, because the way that we are planning to phase converge is by using a beacon lock system. So this is a key element in the program. Is in order to phase converge, we want a reference phase front, and that reference phase front is provided by a beacon either on the target, which in our case is a spacecraft, or nearby within the isoplanetic patch, if we're ground-based, of the outgoing spacecraft. So there's all kinds of other technical problems there, relativistic wavelength shifts, et cetera. But we're kind of slowly knocking down the poles that we see that we can knock down. I can't knock down the economic pole, because that is out of my control, but is in the control of the exponential growth of the photonics community.
There's not a single, and when I say not a single photonics technology that you didn't mention, we're not talking about, optoacoustic endoscopy here for this system. Metrology, yes. Materials, yes. Lasers, certainly. Directed energy, right? Your system involves all of these: adaptive optics, regular optics, at such a high level. And yet, research on R&D is taking place in all of these areas, and that has to be hugely beneficial to a long-term project such as this. In contrast, again, is the biology side. And Joel, you've said, give us a week, give us a year. You could send some of these invertebrate organisms into space fairly quickly. How's that a possibility?
Well, the whole reason these organisms are worked on is because of their small size and their very short generation time, their rapid development. The first means that you can really study them in totality using biophotonics. You can really look at every single neuron, for example, as it's firing when they're thinking. These little guys have only 200 to 300 neurons as opposed to 10 to the 12 that we have. So their small size is, it's fantastic to take advantage of in the lab because we can get information very deeply. Their short development time means that we can look at transgenerational effects. That is, the kinds of inheritance that occur from one generation to the next in a very short period of time. If you work on a mouse, for example, you need to wait 6 months to go from one generation to another. In 6 months, we can go 100 generations pretty much. And so what that means is that we could put together the biological experiments in a ridiculously short period of time if we simply had the right microfluidics device to load things into and the proper optics on board. Sorry, Phil, but we're getting a little impatient here.
Yeah.
just slackers.
No, seriously, our technology, it's all established. It's our part of the project is very simple, pretty much. I mean, it's we could do thousands of experiments and set them up, plan them out, get them set up in a matter of a month.
We spoke about the biological piece of Project Starlight with Rothman on our last episode, which is important for granting context to this work. Microscopic organisms launched into space provides the ultimate visual. Our question about context for Lubin is a bit more obtuse. We wanted to know about precedents, specifically where he might look for a kind of roadmap to chart a course towards project completion. In this setting, the one pillar at a time approach applies to fundamental practical photonics application spaces. Lubin draws a parallel to the semiconductor industry.
There was very much a roadmap in the semiconductor industry. So we have a roadmap for this photonics project, which is rather specific to what we're doing. But what we point out, and it is really important to realize, is that at each level of technological evolution, that there are important application spaces that can be filled. So some things that are low-hanging fruit are, for example, we have a NASA program at the moment to develop a prototype for a lunar rover to explore a permanently shadowed region, which is a crater near the poles of the moon that don't get sunlight. And so they're really cold and may have water, frozen water, as well as other things that are frozen at the low temperatures involved. And one way to power the rover we've proposed is to power it by beamed energy, or directed energy is usually used in slightly different context, but same thing. So it's power projection again, but on a short scale. So things like that. Hey, I want to power a rover at 1 kilometer, 10 kilometers away on the moon. I don't want to run an extension cord, and I don't have solar around to help me. I could put an RTG on board, a radioisotope thermal generator, but that's really expensive and problematic. So can I use beamed power? So we said, yeah, of course you could do that. And so we have a program like that. So that's a very low hanging fruit kind of level, but very practical. Then you ask, well, maybe I want to send power over, say, 100 kilometers from tower to tower on the moon. Okay, yes, we can do that. It may not be the practical thing to do. Where it really starts to get interesting is just ask the question, suppose I wanted to keep a spacecraft up in orbit longer because it's being dragged down by the Earth's upper atmosphere. And in space, for low Earth orbits, that's an issue. The International Space Station, for example, has to be boosted up periodically to stay in orbit so it doesn't come crashing down. And there are other assets where you want to have them at low altitudes relative to the Earth for reconnaissance or other things. And one of the problems is, how do you keep them in orbit? So a kind of another low-hanging fruit, but a space-based one, is to project power from ground to low Earth orbit, which is relatively close. Say over ranges of roughly 1,000 kilometers or so, depending on the slant range, and have an ion engine on board. And your solar array that you normally use can also be reconfigured with proper semiconductor junctions into a laser conversion array, which can have quite high efficiency. We have another program for that. And then you power your ion engine to keep you up in orbit longer, so you don't have to carry a lot of chemical fuel with you. Those are examples of very practical things to do. Then you go out further and say, hey, I have a geo asset that needs more power. Maybe I could beam power from the Earth to geo. Okay, it's a little bit further. And then you say, well, hey, could I beam power to the moon? Yes, we can do that. And then you start working your way out and have these what I would say very practical, very much solving a problem that exists with this same technological core, but just expanding it as you go and keeping track of the economics as you go. So, for example, to run the lunar rover is a very straightforward, very economical, does not require billions of dollars of development at all. You're talking about a program where the source literally fits in your hand, and the optics are basically the size of your hand or less. And the costs are not high at all. And it's much cheaper than running a large extension cord out and dragging it around. It's just much, much more effective. So that's the space where we want to look at applications which will solve problems, real problems, with the core technology that then allows us to develop that core technology into these much more, sort of grandiose visions of eventually enabling relativistic flight. But along the way, you have all these sort of off-ramps, if you will. So if you think of it as a roadmap, and there's lots of off-ramps, and those off-ramps are application spaces. That's how we see the project developing. Now, I don't print money, unlike our federal government that does, and my Xerox machine doesn't work very well. And so it's really an issue of keeping people focused on not just the long-term vision, but the practical applications of what's enabled when you can project power over large distances. So whether it's running a drone in the Earth's atmosphere, either from the ground or from space to high altitude, or it's running drone to drone power or space to space power or ground to space. But you have all these different combinations that we've pointed out in our papers and in proposals, that this is a natural technology to evolve. And it has this wonderful, extremely large industrial and consumer base pushing it. So NASA doesn't have to fund the photonics base to develop new technologies.
When looked at as a series of individual innovations that must take place over time, Project Starlight fragments into a network of achievable milestones. To paraphrase Fred Hampton, theory is great, but it's nothing without practice. Is this just a theoretical possibility, or is it a real one?
We see the signs pretty clearly that point to you can do this as long as you can solve these core fundamental problems of, again, phase convergence, things that bore people. Then we believe this technology is inevitable to be brought to fore, keeping people focused on a singular goal of interstellar capability. In our minds is the wrong approach. It is, let's look at what happens when you can project power over large distances in large amounts. What does that do for you? And the answer is it does a lot for you, and it's something that you want for completely different reasons than have anything to do with interstellar capability.
So where these two very distinct lines of science, biology, and I suppose I'll say interstellar stuff are coming together is on these single millimeter crafts. And that's something we haven't talked about yet. The actual craft that these single cell organisms are going to be, not single cell, these very small organisms are going to be housed on. And they're microfluidic chambers, I understand, and work on microfluidics is happening all the time, right? It was just today, I think, that advances to liquid marbles, a new paper came out of Griffith University, a way to non-invasively refill liquid marbles. My point is that this technology itself is just one more area of science that is apt to advance. Can you tell us a little bit about the craft themselves and how those might be architectured and how those might function when they're out of orbit?
All we need is good on-chip imaging, which is already available now. By the time these things would go up, it would be even better. So that we can do direct imaging of the organisms under a range of wavelengths, visible light plus ultraviolet. So we can use, for example, fluorescent proteins that label, or fluorescent markers that label neuron activity in cellular structures, and a way of, which is trivial, of keeping them frozen. So that's easy because it's cold out there, and then just warming them up at the right time in the small amount of liquid that we put them in, along with their food. And that's pretty much mostly what we need, a little chamber to follow their behavior, for example, to watch them move to an attractant, chemotaxis, to move to an attractant or move away from an attractant, and to test the memories that we've trained them, the training that we've done before we send them up, to test how well their memory performs after that. So really the microfluidics capabilities that are needed are already there. We actually work with other colleagues on campus here to, in fact, I'm just meeting later today with a microfluidics expert to apply that to other problems that we're interested in with these organisms. So from our standpoint, the engineering of the biological lab is straightforward. I think probably the bigger problems, Phil has an enormous number of problems on his plate, but I think the laser comm is a big problem, of course, because we don't want to get lots of information and then can't get it back to Earth. But again, that goes, Phil's bearing all of the weight on the challenges. The biology is straightforward. As I said, if we had a chip in our hand right now, we could send stuff up in a few weeks and ask a lot of deep, important questions.
And so one thing that I'd like to emphasize to your listeners is that while we are to some extent stereotyped into, wafer scale spacecraft, and it's our fault because, we pointed that out as a sort of a natural long-term part of this program for relativistic flight. That's more of an end goal than, say, a intermediate goal. So intermediate systems might be even much more interesting for Joel's use, is that they would be larger, slower, but easier to construct. To get to the same speed, they take more power. So you would go slower just because building, the large infrastructure for launching these things, which can be used indefinitely, by the way. I mean, it is a solid state device, so it lasts for many, many, many years till a lightning strike hits it or something, wipes out part of it. And that there is a misconception too that you leave the laser on for the entire length of the journey. That's not true. The laser ray is only on during the ballistic boost phase, and then you turn the laser off and do the next launch. So in the case of the very small spacecraft that we envision for these ultimate interstellar capability flights, which are flyby missions, by the way, the laser may be only on for a few minutes per launch, and then you have the next launch. But again, this is part of that roadmap I mentioned, is that it's hard at the moment to build an entire spacecraft on a wafer, not so much because we don't know how to put lots of transistors on wafers, we do, But if you read our papers, there's all kinds of issues involved, including communication systems. We have a number of papers on communications over vast distances using low power because you don't have a whole lot of power on board. What kind of power source do you have on board? So one option is a small RTG, radio thermal generator. It's all kinds of issues with that. So yeah, this idea that we are, a star chip or a wafer scale spacecraft is one of the capabilities that we would have in the long run. But along the way, it might be a CubeSat-sized object, or it could even be a Voyager-sized object, or it could be an ion engine-driven object. And that's important. I know I keep emphasizing this, but this whole idea of how do you roadmap something so it's practical and achievable is incredibly important. How do you also make it multimodal so you can use the same system to drive essentially anything from a wafer scale spacecraft for relativistic speeds to humans to Mars? And you can use the same system. That's one of the beauties of this kind of technology.
Rothman and Lubin won't outlive this research. It isn't possible, and as Lubin says, that isn't even the right way to chart the course of failure or success of the work. So how will the success of this collaboration be measured? Will it be by checking off more boxes than are left unchecked? By hitting some arbitrary number of benchmarks? By publishing another 100 papers? That way of thinking deviates from the present day, which, for Lubin, renders it inherently less beneficial than this fundamental question. If I have just one problem, how can I find its solution?
This does attract a lot of people, and both on the public side, because this vision primarily from books and movies of achieving interstellar capability and going out exploring. Except the reality is it's really, really difficult to send humans. Humans are fragile and not the greatest creatures to be sending out, whereas Joel has these amazing creatures that can just, chill out for, as many years as you want, and then, take a little warm cocktail or warm tea and come back to life. It's just, I still am amazed by that, to be honest. So again, yes, there is a roadmap, and one of the end goals, although there is no end goal really in this technology, it just keeps going on forever. But one of the quote end goals in this game is to get to relativistic flight with small masses. But the same technology can be scaled to relativistic flight for large masses too. It's a question of scaling. It's all a scaling issue. So just want to inject that somewhere so that people don't walk away and say, it's going to take those guys 30 years, call me in 30 years when you're done. That's not the right approach to this problem. The right approach to the problem is, oh, yes, I see these great visionary goals in the future. I'd love to do that. What can we do now and in the near future to solve a problem that I have? That's what I want people to be asking, because then they will keep their interest for the long term, just as, gee, it'd be neat if I had a device I could hold in my hand like a tricorder I saw on Star Trek or Dick Tracy. I'd like to have that thing. Well, we have that thing today, more or less. And people say they yawn, right? Because it's just, ordinary. So we want the extraordinary that we wish to accomplish to become the ordinary, because it's just part of our technological evolution.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.